Hey, what's up, guys? This is Chung again. Okay, so today we're gonna talk about this problem. Okay, number 169, majority elements. Right, it's labeled as easy. So today we're gonna talk about a few solutions. Yeah, on how to solve this problem. Right. It's an interesting problem, even though it's easy, but I think it's worth talking about it. So basically, you're given like input of arrays, and so one of the element appears more than half of the length of the array, more than half length of the array. So basically, for example, this one, the length is 3, and 3 appears twice, right? 2 is bigger than 1.5, so 3 is the result. And for this one, right? Uh, 2, 2, 2, 2, right? There are like 4 twos and 3 ones, and 2 will be result. And you can assume the array is non-empty and the majority element always exists in the array. So which means there always be like the one element that have the will have the occurrences more than half of the size of the array, right? So the first solution is it's just to you to sort this array, right? So you sort this array and then you get the sequence the element by getting this the integer from this divided 2. So that will be the our result, right? So it's very easy. Now nums dot sort, right? We sort it, right? Then we just return the nums dot let's see, n equals to the length right here. We divide it by 2, right? Uh, sorry, since this is going to be the index, so we'll be using flooring here, right? So that's it, I think, right? I think it should work. Cool. See, it's very easy. We sort it, and then the element from at this index of the half of the index will be our result because that element will be a will be appearing more than 2 times, right? Sorry, more than half of the array. So what does it mean? It means that no matter how many elements in this array, right, that will to the middle one, right? So the middle one, the middle one will always be our result because since we sort it, right? So if this element is the smallest one, so it will start from here from 0, right? And until m and over m is here, right? If this element is a bigger number, right, and then it will uh, switch uh, to the right side, but still the middle one is still the our result. Okay, so that's the first solution, and the second one is the no, we can use like a counting, right? I mean, another way is to use a hash map counting, right? And in the end, we just get the from each from the hash map, we just get which one has the biggest one, the biggest node, right? The biggest count. And oh, so this one gonna be the n log n, right? Since the sorting is the time complexity is n log n. And but now I want to talk about another one. It's called I think Moran voting algorithm. So basically we have the candidates, right? Candidate and count, right? So what does this mean? So if the candidate is it's a none, right? We just so what does this solution do is every time we see a number, right? If it's the same as the candidate, then we increase the count for the candidates by 1. If it's not the candidates, right? We just we decrease the count by 1. And if the count is 0, we set the current number as the candidate, right? for n in nums, right? If not candidate, right? If not candidate, what do? We set the current number to the candidate, and then we just increase the count uh, by 1, right? Else if, right? Else if the candidate's not null, and else if the number equals to the candidates, right? If it's the same as a candidate, we simply increase the count by 1. Sorry, it's not a candidate actually. It's count if the count is 0. Yeah, if count equals to 0, and then we reassign the candidates, and then we increase the count by 1. So else if the candidate is the same as the current number, we increase the count, right? Else, right? Else we do what? Else we decrease. We decrease the candidates. We decrease the count, and in the end, the candidates will be our result. See, cool. So in this and count, basically every time when the count is 0, we know, okay, now we need a new candidate, right? Otherwise, if the same, we increase the count. If it's not, we decrease the count. In the end, we have a candidate here. Sorry. And the time complexity for this one is it's O(n), right? Because we're only looping the numbers once, and the space complexity is O(1) because we're only using those two variables here, right? We're not using any arrays or lists or anything like that. Okay, cool. So that's that. And the third one solution I want to talk about is called the bit manipulation. Right. So I think bit manipulation is a little bit tricky to understand. I'm also start learning it. And so for the bit manipulation, so what do we do here? First, we're gonna have like array here, right? We're gonna have array of length 32, right? Why? Because an integer in Python, the length of an integer is 2 to the 32, right? That's the biggest integer we have. So with bit manipulation, what we need is for each number, right? We'll break it down into its bit value. So what does it mean? So for 3, the bit value is 1 and 2, right? For 2, it's just 2, right? For 3, it's also 1 and 2. So what we do here, so for each of the bit of inside of this each number, we'll be counting that frequency of that bit value, right? For example, here, let's assume this is like the bits at the beginning they're all 0, right? And for 3, the bit value is 1 and 2, right? So this is the index, right? So the index of 1. So what does it mean? So for 1, it appears once, right? So this count means the count of the bit 1. So we're gonna have 1 here, right? And then 2 is this one, right? So we'll have 1 at here. Oh, so have 1 and 1 here, right? And how about 2, right? 2 is just 2. So we're gonna have like this one gonna become 2 here, right? 3, same thing. 3 is the also 1 and 2. So we'll keep increasing this count here. So it's gonna be 2 here, and here will become 3, right? So, and once we have the count of each bit value of all the numbers, right? So how can we use this? So we just loop through all the arrays here, right? And we check the count of each bitwise here. And if that bit bit value count is bigger than this n divided by 2, and then we know that bitwise is part of our results, right? Because we know that, because that's, like I said, the number will be split into each bitwise, right? The bit value here. So in the end, all the bit number that has the count greater than n divided by 2, each will give us our final result. Okay, let's try to code this. So we're gonna have the bit bucket here, right? Bit bucket, right? And at the beginning, each of them is 0, right? At the beginning, each of the bit count is 0. So we're gonna have 32 here. And for each numbers, right? For each number, number in nums, right? What do? We do a I, right? Since we're going to track each of its bit value. How are we going getting each of the bit value out of this number, right? So we basically we loop through the to range 32, right? 32, and then the bit bucket, right? Bucket I, right? That's the position of I here. Will be the n. We do it like this. How do I call this one? That's the the shift operator, right? So we shift it by I, right? So and then we'll be getting the numbers of I, right? And then but we also need to like do an AND operator with 1 to get the count here. So basically we're getting a 1 here, right? Uh, so okay, so how does this thing works, right? Okay, for example, okay, I will give you an example here. So let's say for 3, right? What is the bit value of 3, right? 0, 1, 1, 0, right? And what we are trying to get here is we are trying to get this 1 for the let's say we have a bit bucket here, right? So 0, 0, 0, 0. Okay. Basically, what we are trying to get here, we're trying to get we're trying to get this 0 here, right? This 1 and 1, the position of that, right? Assuming this, and so n uh that's the shift operator, right? So we're shifting from 0 to 30 to 31, right? So that we can get each the position of the 1 here. For example, with 3, right? So n shift 0, right? What is that? Same, right? Same value here, right? Same value, right? And then basically we're not shifting anything, right? And then why we need to do an AND with 1 in the end, right? Because okay, for this 0, right? The 0 place doesn't have any 1 here, right? So we shift 0, it will be the same, and we do an AND 0, 0, 0, 1, right? For 0, 0, 0, 1, and the AND, what is the AND? AND is equal to, so and as long as there's 1 0, so the value will be 0. So that will be 0, right? So that's what we have. We have 0 here. That will give us 0, right? And now, so this will be 0. Now this I equals to 1, right? 1 means what? We shift this number on the right side. So this one going to become 0, 0, 1, 1, right? Because we're shifting this to right, right? So now, okay, we see a 1 here, right? But we don't want to the reason we're doing the and here, right, is because if we don't do the and here, what do we have here? We'll have 3 here, right? We'll get 3. But since we're doing the count here, this and 1 will give us the count. Will give us 1. Either way, will give us 1 either way because we don't want the actual value. We just want to get that 1 count of this 1 here, right? Because okay, so once we shift to the right side by 1, and we're getting this one, and then if we like do an and with 1, right? What will give us? So basically 1, right? So this 1 will guarantee as long as we have 1 in the at the rightmost position, we'll always get 1 here, right? And we have I here. That's how we set this 1 here. And same thing here for the number 2, right? And when we shift again 0, 0, 0, 1, right? So now it's that 0, 0, 0, 0, 1 because we shift this one more, and when this one get and 1, we also get 1 here, right? So basically that's how we set these things. And so after finishing this for loop here, we'll be having all the frequencies on each beat position, right? And then in the end, so after this one, we just need to loop through the bit bucket, right? So it's not bit in bit bucket, right? Uh, I dot bit count, right? Numerate bit bucket, right? So what do? We just do and then we have an answer here, right? Answer equals to 0, right? So we check if this bit count, right? And we'll also have like a length, yeah, and the length of this arrays here. If this bit bucket its count is greater like that than the divided by 2, right? Then we know this bit position is it's one of the our answer, right? So what do? We do uh, since we have the position, right? So what do? We do and the current position is I, right? And the current position, if we want to convert it back to to the 10 base number, what do? We do a 1, right? And we shift it left to the left by the position, right? Then that's the number of the answer here. And then in the end, we just return the answer here, right? But okay, I think that should do it at least for this one. Uh, in range, at least for this test case. But since we're doing but one more thing to be noticed that since we're using Python, and Python has this like kind of like overflow something auto conversion, basically if if this answer is greater than the biggest number of this one, it will automatically convert to the long type. Basically, if the answer has this, okay, I think I will just run this to you. I'll just run I'll just try to submit it, and then you guys can see the arrows here. Yeah, so that's the issue here. So you know basically, if the answer is like we return the answer if the answer is smaller than the 2 to the right, then that's our answer. But if this answer is greater than the then this number here, we just do what? We just do a like conversion else. Yeah, we do a else here. We do a else what? We do use the answer minus the 2 to the 32, right? Yeah, because the the Python has auto conversion. If it's bigger than the other one, it'll be automatically convert to the long type integer, so that we have, in order to match the output of this problem, we have to do a check here, so that we can convert to this one. Yeah, because at this moment, at this moment, so this answer, right? The answer here will become the positive this number, and this positive number is it's greater than this one, so we have to do a conversion. That's how the bit manipulation works. If this answer was like exceeds the biggest negative integer in the Python, right? In that case, Python will automatically convert this one to a positive one, right? We can do this one. We can do a check here. So let's say if we do a debug here, right? See what's the number? So that's the number, right? And then once we do a bitwise of for this number that exceeds the 32 range, right? And then in the end, the answer will become a positive of this number, so that we have to okay, see the answer will become a positive one. So in this case, but we need to to convert it back to the previous one, because like I said, the Python will automatically convert to a long range, right? So that's what we need to do, a tricky sanity check here. And with that, I think that should work. Yeah, cool. Yeah, seems like this bitwise manipulation is not that fast, because we need to have like 32. We need to have a for loop here, right? Nested for loop and then a second for loop. Yeah, so it's gonna be like what? The n times 32, right? So it should still be like big O n time complexity, and here's like another like O32 is like constant time. It should be like the same like big O(n), but since we have this bit like 32 uh, a loop here, that's why I think it's a bit slower here. All right, cool guys. Thank you for watching this video about this problem and some introduction about the bit manipulation. And I hope you guys enjoyed, and I'll be seeing you guys soon. Thank you. Bye bye.